Well, let's accept that there are people who want something done and that it is a serious problem. What do you think should be done, and how should it be done?
I'm afraid I'm earnestly of the opinion that outside towns do need defending. They're very valuable. But outside the towns that are on the coast, we should learn to live with the erosion, and we should simply be prepared to compensate people, at least after a period of time, who have to move and so on. I mean, in America, they think nothing of jacking up these houses and moving them back.
Each step I'm taking represents the amount of land lost to the sea each year. But the cost of sea defences is enormous. It works out at about £5 for each millimetre of protected land. Hornsey, a small town just north of Mapleton, has been protected at a cost of £7 million. But if the entire Holderness coast were to be defended, the cost is likely to be £200 million. Fighting hard to get protection for his threatened farmers is NFU Group Secretary Richard Babington. With costs like these, it does seem an unrealistic proposition.
That is quite correct, and nobody is expecting them to give them a blank cheque. But at the same time, especially with regard to Mapleton, there is a whole village under threat there, and it's a whole community, and a very close-knit community. The whole community in Holderness is a very close-knit community because it has been so isolated until comparatively recently. So I don't think you can dismiss the personal aspect of it at all, but they realise the harsh reality of what is happening, and nobody's asking for a seawall the whole length of Holderness. We know that's impracticable.
David Kilpatrick at Humberside County Council has the unenviable job of planning and funding sea defences. Some say coastal erosion should simply be allowed to take its course. Deep down, is that a view he shares?
I share it partly, but I have got to look at a more positive side in that nobody has actually tried ever before to stop it. This is the first time that anybody has taken a positive and in-depth look at how erosion is taking place and the kind of engineering structures that might be necessary to arrest it.
This all boils down to finance. Now, what does the law say about the availability of money from government sources or local councils or whatever?
The situation is, I expect, ultimately fair. If a place is threatened by the sea, and if the value of the property, including roads and things like this as well, is greater than the cost of the defensive work, then the government is prepared to give a 70% grant to the local authority to have that work built. It is then up to the local authority to raise the other 30%.
To be realistic, wouldn't it be simply better, cheaper to move people away from that coastline and settle them somewhere else?
Well, if you're prepared to go onto the coast and ask that question of the people who live there, I think you would get the answer fairly automatically. This is an area, it's been forgotten for centuries. It's one of the most forgotten parts of England, I would say. But it has got a very real life, a very real farming life, a very real country life. And anything that can be done to protect it should be reasonably be done. But if I fail to produce a solution, then there is no doubt that the coast will continue to erode. And that all the people who live down that coast, be it in towns or villages or just on the farmland, will have to take the full consequences of erosion.
You've travelled widely around the world, and it's obviously a global problem. Other countries, Holland for example, they would do something about this. The government would do something. Why aren't we?
Well, Holland are protecting lowland, and that's a wise thing to do because they're protecting it from flood. And I'm certainly not against protecting low-lying agricultural land from sea flood. That's very wise. But protecting cliffs is a mug's game. Cliffs are a source of sediment. The sand and gravel in these cliffs is worth far more to the beach than it is to the farmer who's farming on the top. And society should compensate him and accept the free feed of sand and gravel, because we all like sandy beaches, and sandy beaches come from cliffs in this country. The sand doesn't come from anywhere else.
How willing do you think the government will be to compensate farmers?
Well, it ought to be willing, because it should in the end be cheaper than spending money on sea defences. I mean, there's £1 million worth of tropical hardwood being driven into this beach at the moment. £1 million that could be spent usefully somewhere else. And if you paid this farmer £500 a year compensation, he'd be very happy indeed.
These coastal farmers, wouldn't it be cheaper simply to compensate them to go elsewhere?
From a theoretical viewpoint, that would probably seem to be the easiest solution, and then just say goodbye to Holderness. But working in Holderness, it is a particularly good farming area. There's a very, very high proportion of very intensive and very good pig farms. The yields of grain and oilseed rape in this area are way above the national average. So it is a particularly good farming area, and I don't think you can write it off just like that.
It's changing annually. There's no stability about the job at all. It's like farming in general, but the idea was that there would be something to pass on to the lads when I'd passed on. In other words, it'd be a little bit better for them than probably it was for me in my day.
Looking ahead to 30 years' time, perhaps, what do you think the situation will be then?
It'll be just such a lot worse. There'll be such a lot less farmland to work. Just so little left.
There are some people who say that you should be compensated and simply move out. What would be your view to that?
Well, I think we would have put an awful lot of effort into building this up for nothing. How could you compensate that? Our home would have gone, and the business and everything, really.
There is this other thought that you could take part in the set-aside scheme and put some of your land out to that?
Well, I think some of it is getting set aside now, going into the sea.
Short-term defences are not the answer. Some long-term solution must be found. Currently, plans are afoot to create an offshore reef made up of coal waste. It has the virtue of costing next to nothing. But nobody really knows if it'll work. The power of waves can be felt 10 metres down. So what's to stop the artificial reef being flattened and dispersed? If it doesn't succeed, Mappleton will disappear from the map, and cities like Hull and Grimsby will have to be re-sited. The prospect is more than most of us can even contemplate.
Let's hope something can be done to save Mappleton soon. With all these daffodils around me, you might think I'm in Holland, but there's no windmills here.
And the grey shades by feldspar crystals. Those colours are called interference colours, and we can use them to help us identify the minerals in the rock. But to do that, you need a polarising microscope. It's fitted with two pieces of Polaroid, one below the specimen called the polarizer, the other one above it called the analyzer, that you can move out of the system if you want to. Now, most people are familiar with Polaroid sunglasses. They cut down the glare you get from reflecting surfaces like water and shiny roads. And they do that because they only allow light through that's vibrating parallel to a particular plane, the plane of polarization of the permitted direction. And there's another effect you may have seen, which you can get with two pairs of Polaroid sunglasses. If I rotate one lens in front of the other, I can cut the light out completely. And that happens when the two permitted directions are at right angles to one another. And that's the arrangement of the Polaroid pieces in the polarizing microscope. Now, in order to show you how to use an instrument like this to identify the minerals in rock-thin sections, I'm going to use a very simplified model of the polarizing microscope. At this end, we've got a light source, two sheets of Polaroid, and at the other end, a TV camera, which acts as an eyepiece. The arrow on this Polaroid sheet tells you its permitted direction. The light passing through that is polarized parallel to this plane. We call that the east-west direction. The arrow on this Polaroid sheet tells you that the permitted direction is at right angles to the other, that's north-south. And obviously, with only one sheet of Polaroid in the system, you get some light passing through to your eye. I can cut that off by putting Polaroid sheet back again, just as with the sunglasses. When the Polaroid sheets are in this position, we say they're crossed. Now, the air between the sheets is isotropic. Like all gases, it has no effect on the passage of polarized light. If I move a sheet of glass about between the Polaroid sheets, again, there's no effect. Glass has no definite crystalline structure, it's isotropic. And in fact, you'll find there are a few crystalline minerals that are isotropic as well. But the great majority of minerals are not isotropic. This is a sheet of the mineral mica. This rectangular shape we got by cutting from a larger cleavage piece. Now, when I move this about between the two sheets of Polaroid, some light very definitely gets through to your eye. The mica interacts with the polarized light to give you this splendid display of colors. Now, most minerals behave like that if you get them thin enough when you view them between two sheets of Polaroid in the cross position. Minerals like that are called anisotropic minerals. Now, watch what happens when I hold this sheet of mica parallel with the Polaroid sheet and rotate it. It goes dark 1, 2, 3, and 4 times in a complete rotation through 360 degrees. Now, those dark positions are called extinction positions, and they happen at 90-degree intervals. Now, all anisotropic minerals show that effect. All anisotropic minerals will give you 4 extinction positions, 90 degrees apart, in a full rotation when you look at them between sheets of Polaroid in the cross position. And we can explain that if we suppose that all anisotropic minerals, like this mica, can themselves polarize light into 2 mutually perpendicular directions. Let's see how that works. Light coming through the first Polaroid sheet is polarized in the east-west plane. It can't get through the second Polaroid sheet because that only lets light through that's vibrating in the north-south plane. But when we put the mica sheet in with its 2 polarization directions east-west and north-south, still no light comes out of the second Polaroid sheet. The mica's in extinction. And in this position, the mica doesn't affect the passage of the polarized light. If the mica is rotated through 90 degrees, it's again in extinction because its 2 polarization directions are once again lined up with those of the Polaroid sheets. Rotate it a further 90 degrees and we see the same effect. Well, that does seem to explain some of what we see. But now let me show you that anisotropic minerals really do polarize light in 2 mutually perpendicular directions. This is a natural cleavage ROM of the mineral calcite, a special transparent variety called Iceland spar. Calcite is anisotropic. So when I put it over this dot, you see 2 images. You see 2 images because of double refraction. Now the light rays corresponding to one of those images is polarized into one plane, and the light rays corresponding to the other image are polarized in a plane at right angles to that. Now that being the case, I can make those images disappear and reappear by rotating a sheet of Polaroid over the calcite ROM. Now let's just look at that a little bit more closely. That's the permitted direction of the Polaroid sheet. If I hold it over the calcite in that position, only one image is visible. And that must mean that the light corresponding to that image is polarized to vibrate in that plane. And if I turn that through 90 degrees, the other image appears and the first one disappears. And that means that the polarization plane of the second image must be like that. So we've got 2 directions of mutually perpendicular polarization. Now, all anisotropic minerals have that effect, but calcite's the only common mineral that shows it anything like so well. Now, there's another very important aspect of double refraction, and it's this. The light rays corresponding to those 2 images travel along different paths through the crystal, and they travel at slightly different speeds so that one set of rays lags a little bit behind the other. And that lag we call a path difference. And it's that path difference that's responsible for the interference colors that you were looking at earlier. The light that leaves the first Polaroid sheet is polarized into a single plane. When it passes through a mineral that's not in its extinction position, the light that emerges is polarized into two mutually perpendicular directions by the mineral. These are then polarized back into a single plane by the second Polaroid sheet. Now this light's still actually made up of the two rays that travel through the mineral at different speeds. So one ray is lagging behind the other. There's a path difference between them. If that path difference between the two waves corresponds to a whole number of wavelengths, then the crests will coincide so that the two rays reinforce each other, and you get constructive interference. But if the path difference between the two waves corresponds to an odd number of half wavelengths, then the crests of one wave will coincide with the troughs of another, and the two waves will cancel each other out. That's called destructive interference. So the effect of interference is to produce either light or darkness. The first dark band corresponds to a path difference of half a wavelength, the first light band to a path difference of a whole wavelength, and so on. And this is the effect of variable path difference when we use light of only a single wavelength. But in the microscope we use white light, and white light's a mixture of wavelengths. So instead of seeing alternating light and dark bands, you see this repeating pattern of the rainbow colors in the spectrum of white light. This progression of colors is the result of increasing path difference in anisotropic minerals. And in standard thin sections, we keep the thickness constant, so the path difference depends only on the amount of double refraction in the mineral. And in fact, in most of the minerals we're dealing with, the interference colors in standard thin sections will correspond with the lower part of this chart. But you won't see interference colors at all if you can't get rocks and minerals thin enough to see through. And up until about the middle of the 19th century, geologists had to make observations on rocks and minerals using only the naked eye or the hand lens. Till about 1850, when Henry Sorby, a scientist living in Sheffield, found out how to grind rocks thin enough to see through and to mount them on microscope slides. And this magnificent brass instrument is the very microscope that Sorby himself used. And here is one of Sorby's original thin sections. It's of a granitic rock from Aberdeen, beautifully made, and he's even engraved the locality on it and the year in which it was made, 1858. And today, thin sections of rocks and minerals are made by the same methods used by Sorby. There's a large thin section preparation laboratory on the campus of the Open University, which is equipped to make large numbers of slides for students studying geology courses. First, massive amounts of rock have to be gathered. Granites and basalts and many other different kinds of rocks are collected from all over Britain and sometimes from overseas as well. It's very important that the specimens are fresh and quite large so that many identical specimens can be produced. These large lumps are then broken down into smaller pieces. An automated diamond-edged saw is used to cut them into a series of 2mm slices. It's important, even at this stage, to get a slice which has a constant thickness and which is as smooth as possible. The slices are then lapped and cut into smaller slices, ready for mounting onto a glass slide. A warmed-up epoxy resin is used to cement the rock slice to the slide, and it's very important that they're pushed firmly together so that no air bubbles are trapped in the resin. Both the glass slide and the resin are isotropic, so they won't have any effect on the light that passes through them. Now, the next step is really the most difficult and the most important. The rock slice is now ground down in stages to a uniform, very thin layer of about 100 microns. The first few layers are removed with a carefully adjusted surface grinder, which can pass over 120 specimens at once. The thin sections are often finished manually by grinding them face down on a glass plate with a fine abrasive powder, to get a uniform thickness of exactly 30 microns. It's very important to be able to grind any rock thin sections to this thickness so that the optical properties of the different minerals can be accurately compared. And this final thickness is controlled by observing the interference colors of a common mineral like quartz, which is present in a large number of rock types. And if you like, before you put the thin section on the microscope stage, you can look at it between two sheets of Polaroid. The interference colors show up the different grains, and they change as you move the slide about. It gives you an overall view of the texture. This is the main microscope room of the Earth Sciences Laboratory at the Open University. And I'm going to use this rather impressive instrument. It looks rather different from your microscope, but it has exactly the same basic components. The light source, polarizer underneath the stage, rotating stage, analyzer out and in. There's a binocular eyepiece on this instrument, and here a TV camera that's linked to this screen so that you can see what's going on. And that's why I'm going to use this instrument. So let's take a look at this thin section. As I rotate the stage with the analyzer in, you can see at once the irregular interlocking texture of the mineral grains in this crystalline rock. It's a granite. Now, all the minerals in this rock are anisotropic. They all have 4 extinction positions, 90 degrees apart, in a full rotation of the stage. Each grain goes into extinction when its polarization directions are parallel with those of the polarizer and the analyzer in the microscope. And the minerals in this rock are obviously in all sorts of different orientations, and that's typical of a great many rocks. All rocks are 3-dimensional aggregates of minerals. And any thin section through a rock like this granite will give you a 2-dimensional picture of it. And because the mineral grains are in random orientation in the rock, the thin section will cut through them in every conceivable direction. And what I want to show you is the effect that that has on the way that minerals look when you see them down the microscope. Now, with the analyzer out, most of this thin section is colorless, except for these brownish crystals. Now watch what happens when I rotate the stage. They change color between lighter and darker brown. Now that's an effect you see quite often with colored minerals in thin section when you look at them with analyzer out. It's called pleochroism. This is biotite mica, and it's one of the most pleochroic of all minerals. All micas have this fundamentally layered internal arrangement of their atoms and ions. They all have a very well-developed cleavage parallel to these layers, which are planes of weakness in the structure. And this is a large and rather irregular crystal of biotite mica. And you can see the cleavages on this edge. Now then, imagine what you'd see if you were to cut a 2-dimensional section through this mica at right angles to the cleavage. You'll see something like this, a rather irregular crystal